In this video, we're going to discuss about the multi-class logistic regression. As the word says, the multi-class logistic regression aims to conduct a multi-class classification problem in which we would like to predict more than two classes. Examples of this can be predicting different types of weather, such as rainy, cloudy, or shiny, or another example can be the optical character recognition. So in the binary logistic regression, we use the sigmoid function in order to implement the probability of an outcome of an input X belonging to a target class. Now we want to generalize this to C classes where C is greater than 2. So one way to generalize this would be to extend this sigmoid function, and instead of having a single weight like we had in the class of the binary regression, to have multiple weights and specifically one weight per class. So we can have one weight WC per class. If we were to simply rewrite the sigmoid exponential function for each of these WC weights, then we would have had this expression here, which is exactly the expression of the sigmoid function. However, we observe that if we sum these terms for all C, these terms do not add up to 1. And we said that the output of the sigmoid function represents a probability. Therefore, if we were to sum up all these probabilities, then this thing needs to actually sum up to 1. For this reason, instead of using the sigmoid for the multi-class logistic regression, we're going to use another function which is called softmax function. And this function does essentially a very similar thing. It assigns a probability of a given input belonging to a target class C, where C ranges from 1 to capital C. And this probability is going to be equal to this expression. The nominator of this expression is the exponential of the current weight of the current class multiplied by the input space. And the denominator of this softmax function is the sum of all exponentials over all classes. So by using this expression, what happens is that the sum of each of these probabilities for all the classes actually now sums up to 1. And this is great because in this way we can generalize the binary classification to the multi-class logistic regression. So the way that we can represent the multi-class logistic regression is again that we have an input vector X of dimensionality D. We have C different outputs, meaning C different classes, a set of training data of N samples. And then as part of our model, we get a probability of a data sample X belonging to a certain class C, given the weight of that corresponding class. If we were to make a final decision about what would be the actual class that we are going to classify our target sample, we are going to decide based on the maximum posterior probability, on the class that corresponds to the maximum posterior probability. Therefore, the unknown parameters that need to be estimated from our data are the weights that correspond to each of the C classes, W1 through WC. Now, in the next slide, what we're going to show is that the multi-class logistic regression actually can be shown to be the same as the binary logistic regression if we set C equal to 1. So if we only have two classes, 0 and 1. So for this, what we're going to do is that we are going to set a single weight, W1, that corresponds to class W1, and another weight W0 that corresponds to class W0. And then we're going to compute the probability of our sample belonging to class 1, given the weights W0 and W1. If we substitute this probability based on that equation here, from the softmax function, and we substitute the values W1 and W0, then what we can do is that we can multiply both the numerator and the denominator of this fraction by exponential of minus W1 transpose times X. When we do that, the numerator becomes 1 and the denominator becomes in this form. So then if we kind of collect all the terms that are multiplied by X together here, we get this expression here, which is the same as the expression of the sigmoid exponential function. But now instead of having two W's, we can have a single W, which corresponds to the difference between W0 and W1. So essentially, we understand that the binary logistic regression that we learned in our previous video is a special case of the multi-class logistic regression. So a few more things that we have to actually discuss before we are able to solve the problem of the multi-class logistic regression is the fact that we can, in order to simplify our calculations, it is better to conduct a one-hot encoding in order to code the output, the class output. So this means that so far we have denoted that the output is a single number that corresponds between 1 to capital C, where capital C is the range of classes. What the one-hot encoding does is that instead of having a single number for an output, we have a binary vector that has as many elements as the total number of classes that we have for our specific case. And this binary vector only has a single element that corresponds to 1, and this single element is located at the position of the corresponding class of that sample. So, for example, if we have a dice, and a dice always has, in our case, can have 6 sides. So the probability of each side can be denoted by theta 1 all the way up to theta 6. If we roll the dice 6 times, then we can get this, 7 times, then we can get these 7 different outcomes. So the outcomes range from 1 to 6. And in our case, the sequence of outcomes is 1, 1, 2, 2, 5, 6, 6. So if we were to have a multinomial distribution and denote the likelihood of observing the above samples, what we could do is we could transform the observations of samples, so we can transform these observations here into a one-hot encoding, which is being denoted from here. So here we can understand that each of the elements of the one-hot encoding corresponds to one observation. This first element corresponds to observation 1, and this is a vector that has 6 elements. Each element corresponds to one side of the dice. In that case, the result of the dice was 1. That is why 1 is located in the first position of this vector, while the rest of the elements of this vector are equal to 0. If we go now to this outcome, to this third outcome that corresponded to 2, this is the vector that represents this outcome as a one-hot encoding. And we understand that, again, this is a vector with 6 elements. All elements are 0, except the second position, the second element of that vector, that corresponds to outcome 2. Similar, if we are to encode outcome 6, we would have a vector like that, where all elements are 0, except the one that corresponds to the 6th position of the vector. So this is called one-hot encoding, and the reason why it is so mathematically so convenient is that it can be used in these probabilities here. So then, since we can assume that each of these observations of rolling a dice follows a multinomial distribution, the probability of observing observation x1, which is this observation here, can be denoted as this product here. So this product is the product of all the different probabilities of each of the sides of the dice, theta 1, theta 2, theta 3, and until theta 6. And in each of these probabilities, the exponent to which each of these thetas is raised is the corresponding element of that vector. So we see that theta 1 is raised to 1, and all the other probabilities are raised to 0. And that mathematically is really, really convenient. Similarly, if we have the probability of observing the X observation, X3, then we would have all the thetas raised to 0 except from theta 2, which corresponds to 1. And theta 2 essentially represents the outcome, the probability of the second outcome. So that's the probability of observing a single observation, X1 up to X7. Now the probability of observing all the observations is just the product of these separate probabilities. So from here we can have this product, and each of these probabilities is again another product which corresponds to the product of all the thetas raised to the corresponding element of the one-hot encoding. So this results in just multiplying the theta that corresponds to the outcome of that specific observation. Now, similarly, if we use that specific logic and the one-hot encoding technique for our multi-class logistic regression, we can change the outcome of the regression, which it used to be a number from 1 to C, to a vector that has C elements and also contains this one-hot encoding data. So this the elements of the vector all correspond to 0 except the element that belongs to the outcome class C of observation yn. For example, if our sample belongs to the third class, then the corresponding one-hot encoding would be 0, 0, 1, and then all zeros until we reach the number of total classes, which is the length of the vector. So what we would like to do, since we are now having something like a multinomial probability, is that we would like to maximize the likelihood of our data. As we discussed in the case of binary logistic regression, the likelihood of our data is the product of all our single observations. And essentially the product of observing each outcome yn given our input data xn and of course given the weights. This product, this single probability now, if we write this in the form of the one-hot encoding, it can be converted to this expression here. So this expression essentially has C elements that are being multiplied, as many as the number of classes. The first element corresponds to the probability of observing the first class. The second element corresponds to the probability of observing the second class, and so forth and so on. And each of these probabilities is being raised to this element y and c. This is this element of the one-hot encoding vector. So we understand that if we have a sample xn that belongs to the first class, this yn1 will be 1, and all the rest here will be 0. Therefore, this thing here will be just the probability of observing yn1, and all the other products here will be equal to 1, because all the other exponents will be equal to 0. And similarly for all the other classes. So if we are to now compute the likelihood for all our data, it will be the product of the products, and the first product goes over all our data. The second product runs over all our classes, And this probability is the probability of observing the C class, small c, given the weights raised to our label Y and C. And this is the element, the C order element that corresponds to the one-hot encoding of our sample Yn. Now, if we have computed the data likelihood, it's very easy to compute the cross entropy error, which is just the inverse of the logarithm of the data likelihood. And this is how this result looks like. So if we add a logarithm here, and then we bring the exponent in front from the properties of the logarithm, this is how this would look like. And we would use similar optimization procedures in order to minimize this cross entropy error. A very simple optimization procedure that we can use is gradient descent. We can find the gradient vector with respect to each of these weights. And although computational details are out of scope, we see that this gradient vector for the multi-class case is very similar to the gradient vector of the binary classification case. So essentially, the gradient for weight WC is proportional to each of the training samples xn multiplied by this error difference. And this difference here represents the probability of our sample n belonging to class C as computed by the current form of our logistic regression classifier minus the actual label of our sample n with respect to class C. So essentially this Y and C, it's always either 0 or 1. Therefore, this means that if a sample xn, if a given combination of vectors W1 through WC classifies correctly a sample xn, this difference will be small, and therefore the sample xn will contribute less to the new weight of that is results from the gradient descent. Otherwise, if sample xn is quite wrongly classified, this error is going to be large. Therefore, this sample xn will contribute more to calculating the new weight. This is the end of the multi-class logistic regression case. And I'll see you in the next video.